Hello all. I'm happy to welcome you all back to the course U21CH404, that is process heat transfer. So in our last class we discussed about the basic of heat transfer, the various modes of heat transfer like conduction, convection and radiation. So in today's class we are going to discuss about steady state unidirectional heat transfer in plane wall, composite wall, cylinders and spheres. Let us try to cover for plane wall and composite wall in today's class. First, let us decode the terms like steady state unidirectional flow. So what do you mean by steady state? Whenever a property of the system, say like temperature, pressure, flow rate or anything, when the properties of the system does not change with respect to time, then we call it as a steady state. So what do you mean by unidirectional? When the property, here we can say that the temperature, when the temperature passes through and varies only one direction, then it is called as unidirectional. So in our case, we are going to consider it in only one direction, that is in x direction. Considering these assumptions of unidirectional and steady state, a French scientist called Joseph Fourier has come up with a law called Fourier's law. This law is applicable only for heat transfer in, that is conduction in solids. Let us go into the law. The law states that is the Fourier's law states that the rate of heat flow, that is Q, the rate of heat flow by conduction through a uniform fixed material under steady state, that is the temperature does not change with respect to time, is directly proportional to the area normal to the direction of the heat flow, that is A, and the temperature gradient in the direction of the heat flow. The temperature gradient is given by dt by dn. So Q, the rate of heat transfer, is directly proportional to area A and the temperature gradient dt by dn. You can see in the equation 1.1, that is the temperature gradient dt by dn is given a negative symbol. Do you assume why is the symbol is given a negative? It is mainly because as the distance increases, the temperature usually decreases. We can see a negative symbol and this is the main reason behind it. In order to remove the proportionality symbol in the equation 1.2, we are replacing proportionality with a constant called K, that is thermal conductivity. Thermal conductivity is property of a material. So, it is a property of a material to conduct heat. Let us consider an example. Let us have plastic and any metal like steel. We all know that the thermal conductivity of plastic is very poor, but the thermal conductivity of steel, aluminium, gold, any other metal is very good. So in this case, plastic will have a lower value of thermal conductivity and the metal that we have considered as steel will have a very high thermal conductivity. So the value of K will be low for plastics and the value of K will be high for metals. The unit of thermal conductivity is given by watt per meter Kelvin. Now, in the equation 1.2, let us have look into the unit of all the quantities. Q, that is the rate of heat transfer. The unit is given by watts. We know that 1 watt is equal to 1 joule per second. Next one, K, thermal conductivity. As we just discussed, the unit is given by watt per meter Kelvin. And area, obviously we know the unit is meter squared. And finally, the temperature gradient dt, that is the temperature is given by Kelvin and the thickness x or n is given by meter. So now, the Fourier's law can be rearranged to give a heat flux. What is flux? The flow of any physical quantity with respect to area is normally called as flux. So it is very common that we all know. Here, the flow of physical quantity is nothing but temperature. So, the rate of transfer of temperature with respect to area is given by heat flux, that is small q. The small q is equal to heat transfer rate divided by area. The unit of heat flux is given by watt per meter square. Now, let us look into the derivation for rate of heat transfer through a steady state one-dimensional conduction through a plane wall. So before starting this, we should have some basic assumptions for these kind of derivations, right? So the assumption starts with steady state condition. That is, the properties of the system does not change with respect to time. When we assume this and unidirectional flow for any system that undergoes conduction, we can directly apply our Fourier's law. It is given by Q is equal to Ka dt by dx. The negative symbol is mainly because as the temperature decreases because with respect to the distance. So the first assumption in this case is steady state condition and one dimensional heat transfer as that of our Fourier's law. The next second one is uniform cross section of the material. Third one is thermal conductivity is independent of temperature. We know that the thermal conductivity K is a property of a material. In most cases, this particular thermal conductivity will be varying with respect to temperature. But here, in our assumption, for the simplicity of this derivation, we are assuming that the thermal conductivity is independent of temperature. So, it is not going to vary with respect to temperature. And the final assumption, since here we are going to deal with only conduction, we are considering negligible convection and radiation. So look at this diagram in figure 2.1, conduction through a plane wall. So let us consider a plane wall. At one point it is the hot face of the plane wall and other point is the cold face of the plane wall. The hot face is at a temperature T1 and the cold face is at a temperature T2. You can identify that T1 is higher than T2 by the line that passes through the wall, that is a declining line. So the temperature always flows from higher temperature to the heat always flows from higher temperature to lower temperature, that is from T1 to T2. We can also see that at the hot phase, that is T1, the thickness of the material is given by x is equal to 0. And also at the cold phase at T is equal to T2, the thickness of the material is given by x is equal to x2. For any study, we are going to consider only a small element, and here also we are going to consider a small element of thickness given by dx. Now, let us directly apply our Fourier's law for this case. We know that Q is equal to minus Ka dt by dx. So here x is nothing but the thickness, T is nothing but the temperature, K is the thermal conductivity and A is the area of the wall. Here there are two quantities that are going to vary. One is the thickness x and the temperature T. So both the quantities can be integrated with respect to their boundary conditions. So the boundary conditions are at T is equal to T1, x is equal to x is equal to 0 and at T is equal to T2, x is equal to x. So these are the two boundary conditions. Upon integrating the equation with respect to the boundary conditions, we can see that look into the equation 3, integration of dx is given by x and the integration of dt is nothing but T2 minus T1. The upper limit is T2, so integration of dt will give you T and the upper limit is T2, so substituting T2 minus T1. We also have a negative symbol at the outside near to minus k. So we can take that negative symbol inside and the equation can be rewritten as q into x is equal to ke T1 minus T2. And finally, the equation can again be rearranged to have only the heat transfer at one side and every other thing to the other side. Look at the equation 6. You can see that Q is equal to Ka x by del T. T1 minus T2, that is nothing but the temperature difference is replaced with del T here. Next one, look at the equation 7. The equation 6 is rewritten, that is it is rearranged to bring Q is equal to del T divided by x by Ka. And this x by Ka is replaced with R, that is nothing but resistance. Any material will have some resistance for heat flow and this resistance is nothing but x divided by Ka, where x is thickness of the material, K is thermal conductivity of the material and A is the area. So the unit of resistance R is given by, it is a question to you, you guys are going to find and the answer will be discussed in the quiz session at the end of the section. So the reciprocal of resistance is given by conductance. So C is equal to 1 by R. R is x by Ka. So C is Ka by x. So let us look into the think section. The first question is, if the thermal conductivity of the material varies with temperature, which K value should be used? So in this case, we can go either with average K value or average temperature. The second question, what are the properties that thermal resistance and thermal conductivity of a material depend on? We know that resistance R is equal to X by Ka, where X is thickness of the material, K is thermal conductivity of the material, A is area of the material. So these three are the things in which these three are the properties in which the resistance of a material depends on. Similarly, conductance is nothing but reciprocal of resistance. So all the three is same for conductance also. Next, thermal conductivity. As we discussed earlier, it is a property of a material to conduct heat, right? So it is a characteristic property of a material and it is given by the symbol K. So unit is watt per meter Kelvin. By definition, let us look what is thermal conductivity. Thermal conductivity is a quantity of heat passing through a quantity of material of unit thickness with unit heat flow and unit time when a unit temperature difference is maintained across the opposite faces of a material. So this is the definition of thermal conductivity. Now it is the time to think and quiz session of this particular class. Now, on what factors does thermal conductivity depend on? So K is nothing but properties of a material. So thermal conductivity obviously depends on properties of the material. It is a materialistic property. Second question, how does the thermal conductivity of solids, liquids, gases compare it? Obviously, solids will have higher thermal conductivity when compared to that of liquids, and gases will have lower thermal conductivity when compared to that of solids and liquids. Let us look into the third question. What is the unit of heat transfer rate? The unit of heat transfer rate, Q, is nothing but watt. What is the unit of thermal conductivity? The unit of thermal conductivity, K, is equal to watt per meter Kelvin. And the resistance you are going to discuss, the unit of resistance is Kelvin per meter. Thank you for this session. Let us discuss the remaining in the next class. Thank you.